Okay, so good morning and thank you. I would like to acknowledge Professor Ferrante and also Dr. Acopat for the kind invitation to show you some of our results regarding the toxicity and bioavailability of inorganic nanoparticles. So, to move this one. So, as you probably know, nanoparticles, nanomaterials exhibit very outstanding properties. So these materials are mainly used in many products that we use every day. It's quite important the presence of these nanomaterials in cosmetics and personal care products, and also in textiles, and mainly in the food industry. In the food industry, we can find inorganic nanoparticles in the preparation of the packages, the intelligent and smart packages to keep the food, and also as a food additive. So we can find, silica nanoparticles, that is an anti-caking agent and also a carrier for flavors in the food. Also silver and zinc oxide nanoparticles that have antimicrobial properties. And in the case of titanium dioxide, the E171, that is a whitening agent and also provide brightness to food. As you know, this titanium dioxide has been banned by the European Commission, has been banned recently. You can see that it has been proved to be genotoxic, so it has been banned or not recommending as a food additive. Okay, so the problem that when we want to measure nanoparticles in very complex samples, like food, or even after performing several trials to assess toxicity or bioavailability, is that there is not a unique analytical technique that can give us all the properties of nanoparticles. Because in addition to the chemical composition and also the size distribution and the number of nanoparticles, there are other functionalities of these nanoparticles, like the shape, crystallinity, porosity, and mainly the surface layer. The functionality in the surface of the nanoparticle that is going to change toxicity, bioavailability, and in general, the effect of these nanoparticles. Recently, there is a promising analytical technique that is inductive coupled plasma mass spectrometry, working in the so-called single particle mode, or SPICPMS. That is a quite useful analytical technique because we can obtain at the same time the composition, the nature of the nanoparticle, the number of nanoparticles. Also, we can obtain the nanoparticle size distribution and the fraction of metal that is in solution, the dissolved metal fraction. So it's quite useful for this type of studies. So recently, the European Food Safety Agency has published a guidance to evaluate the risk assessment of nanomaterials in the food chain and the feed chain for human and animal health. And this guide is have an update in last year, in June of 2021. This guidance recommends the performance of several trials, like the in vitro gastrointestinal digestion with the biopersistent assays that was similar to the bioaccessibility assays, also cellular transport and cellular permeability in the case that the nanoparticles are present at nanoscale after these procedures. So we have to evaluate the stability in under lysosomal condition, that is when the nanoparticles enter in the cells, and also obviously the evaluation of the molecular responses, proteomics and also genomics responses. So I show you here the procedure, the in vitro digestion procedure that we have used. So more or less there are two parts. The first part that is the gastric digestion, in which we mix the nanoparticles of the food with a gastric solution containing pepsin. Also then we use intestinal digestion that consists of change the pH of the solution and use pancreatine and bile salts as the intestinal digestion, for the intestinal digestion. And as you can see here, we can take the aliquots during several times in the gastric and also in the intestinal digestion stages. So we can calculate the bioavailable and the biopersistent fraction. In the first case, the bioavailable fraction is going to be the ratio between the number of nanoparticles that we obtain after performing the bioaccessibility procedure at the end of the procedure, so at the 120 minutes of the final process. But the EFSA has developed or have proposed a new concept that is the biopersistent, that is exactly the same, but we use the number of nanoparticles after the 30 minutes of the intestinal stage. So it's the same procedure, but we take the values, the concentrations at different times. Also, the EFSA suggests that we have to perform experiment with 3 different concentrations levels at several gastrointestinal times, and also that we have to perform twice a duplicate of the determination of the experiments. And also we have to offer results regarding the particle number concentration, the particle size distribution, and also the dissolved metals. And the guidance said that we have to consider a nanomaterial or nanoparticle as highly biopersistent if this biopersistent ratio is higher than 12%. So we have tested 2 different types of nanoparticles, the titanium dioxide nanoparticles and silver nanoparticle of 2 different sizes. And we tested 3 different concentrations for each one. And also we performed experiment with the food grade, we performed the experiment with the food grade E171, this nano and micro titanium, and also with seafood, mussels, mollusks in general, and surimi, crab sticks. So in this slide, I am going to show you very, very fastly some of the results. So in general, we have obtained that there is a decrease in the number concentration during the gastric step and an increase in the number concentration of the nanoparticles in the intestinal step. And this is because mainly, in addition to dissolution or other phenomena that can occur inside during the process, is mainly because the agglomeration and dispersion phenomena. So as you see here, I am going to show you some transmission electron microscopy images. And you can see here that in the case of a gastric fraction, there is agglomeration. So agglomeration of nanoparticle increase the size and decrease the number of nanoparticles. However, in the intestinal fraction, we are going to have all the nanoparticles dispersed. So the number of nanoparticles increase, and obviously the size of the nanoparticle, the size distribution is reduced. So similar result has been obtained for mollusks, for mussels, and also for the crab sticks. And the same, we are going to obtain, we are going to obtain agglomeration in the gastric fraction and dispersion of this titanium dioxide and silver nanoparticles during the intestinal step. Okay, so if we consider this value, this concept of the biopersistent, we can calculate the biopersistent ratio of the different standard and also the biopersistent of these nanoparticles inside food. And we have obtained values, very high values, in the case of titanium dioxide nanoparticles, that you can see that are close to 100%. And in the case of silver nanoparticles, the standards, we obtain moderate biopersistent ratio in the case of the nanoparticle of short size, but high percentages in the case of the large nanoparticles. In the case of the food grade E171, we obtain a ratio close to 100%, and was the same for crab sticks. You know that surimi, to see the meat white color, contain this type of food additive. So the result is the same, more or less 100% of the biopersistent when we perform the experiment with this type of food. However, in the case of seafood, the biopersistent is lower. In the case of silver nanoparticle, it's about 9%, and although there is not in the screen, in the case of titanium dioxide is between I think that lower than 20%, between 7 and 20%. So you can see here that the matrix influence enormously this result. So it's not the same that we are working with the standard, that we are trying to evaluate the effect of the nanoparticle that previously has been incorporated naturally or artificially in food, in food. Okay, so I want to show you here other experiments, in this case regarding bioavailability of cellular transport. So we have used a CACO2 model. We put this CACO2 cell monolayer in this transwell device. So we load the bioaccessible fraction in the apical chamber, and after performing a series of procedures, normally is incubation at 35 degrees centigrade for 2 hours, we are able to collect the basal fraction. So we can establish the transport, like a ratio between the number of nanoparticles in the basal chamber and the number of nanoparticles in the bioaccessible fraction. So we can obtain the amount of nanoparticles that are able to cross the intestine barrier, and we have obtained that in the case of titanium dioxide nanoparticles, about 1782% of the nanoparticles can cross the membrane. So are shown for mollusks, so mussels, clams, etc. And lower transport can be obtained for silver nanoparticles. You see here that is lower than 22%. So the titanium dioxide appears to be more bioavailable than the silver nanoparticles. So if we focus our attention on the sizes, we can see that there is also changes in the size distribution. So in the case of titanium dioxide nanoparticle, we can see that the sizes are the same in the bioaccessible fraction and also in the apical fraction. Here is the apical fraction, the apical fraction after performing the experiment. However, the size distribution is lower in the basal fraction. And similarly, the results are the same for silver nanoparticles. Sorry. And again, in this case, we obtain that the agglomeration dispersion phenomena is quite important. Sorry, I don't know why. Here. So you can see here that in the case of the bioaccessible fraction and also in the apical fraction, there are more or less agglomeration. However, in the case of the basal fraction, there is more dispersed nanoparticles. So regarding the dissolution, the possible dissolution of the nanoparticle during the procedure, we cannot be sure because in addition to this phenomena, we have to take into account the agglomeration and the dispersion phenomena because nanoparticles depend on the environment. So it's quite difficult to say that during the transport there is a dissolution or this ionization of this type of materials. Okay, so we have verified more or less that nanoparticles are bioaccessible and can cross the membrane, the intestinal membrane, so they can reach our cells in our organism, and we have to evaluate the stability under lysosomal conditions. So the EFSA established a simulate lysosomal fluid. You have here the composition, so it's a very complex solution. And we have tested two types of nanoparticles, titanium dioxide and silver nanoparticles at two different size distribution and also at three different levels. And also we have evaluated the food grade E171. So we subject the solution to incubation at 35 degrees centigrade, and we take the aliquot several times, 24, 42, 48, 72, and 96 hours for analysis. So we can see here the results regarding the number of nanoparticles and also regarding the mass, the metal mass. So we can see that in the case of silver nanoparticles, there is a gradual decrease of the number of nanoparticles during this experiment. And this degradation is more evident if we express the results in metal mass. That is the graph that you see in the right. In the case of titanium dioxide, it was quite similar. So we can see a decrease in the number of nanoparticles, but we can see a plateau here. So it's like after until 28 hours, the number of nanoparticles remains constant. There are no degradation. And finally, in the case of the food grade, we have obtained that there is no degradation. You can see here that the number of nanoparticles is exactly the same during all experiments. So this implies that this food additive is not degradable under lysosomal conditions, and that we can obtain the nanoparticle after a very long time inside the cells as nanoparticle or as microparticle, because this food grade additive contain both types of nanoparticles. However, in the case of the titanium dioxide nanoparticles, there is a degradation until 50%. So more or less is a moderate degradation. And in the case of the silver nanoparticle, the degradation is higher, it's about lower than 20%. So we can assume that there is more or less degradation inside the cell in the case of silver nanoparticle, and moderate in the case of titanium dioxide nanoparticles. So, as conclusions, we can say that titanium dioxide nanoparticles are high bioaccessible and high bioavailable, and also that the stability under lysosomal conditions is also very high. In the case of silver nanoparticle, this bioavailability, this degradability is less important. However, we have to take into account that the matrix sample have a great influence, so can be different totally the result if we use a standard, we use a food, or we use another type of food. Also, I want to say you that we need improvement in the analytical techniques that we use for the evaluation of this type of experiment, because in the case of the standard is not a problem, but in the case of real samples, the number of nanoparticles is very low. So we need very robust analytical instrumentation and also very good quality standards to be sure that the result that we are giving are accurate, with the most accuracy. Finally, I would like to acknowledge my research group, the GTEE, and my institute, the IMATUS, also the funding that we have received for performing this type of experiment, funding from the local and national government, and also from the European Commission. And obviously, thanks all of you for your kind attention.
Thank you very much, Professor Moreda, for this very interesting and keen presentation. And we go to the next keynote speaker.